Okay, now we're recording. Good. All right, so, but of course the blackboard won't be. So there's a question which was asked about, which from the slide, from the previous tests and stuff, that converting, how to convert a DFA to a regular expression. And there are a bunch of questions like that. We just haven't gone as far as we should have so far. So there are definitely things that we haven't covered, and that's one of the things we haven't covered. All right, so if we haven't covered it, then it won't be on the test. All right? That's fair, right? So, but here's an ugly regular expression that comes up, and so we can think about understanding what strings it produces. So let's first do this one. Everybody look and think, what's the set of strings that this guy produces, and what's the set of strings that this guy produces, and are they the same? Any thoughts? Everybody think they're the same? How many people think they're different? How many people need to study more before this test? Excellent. Excellent. So the way I would think about this is, let's try doing the parse tree, right? So let's look at this guy here. What is it? It's the concatenation of four things, right? And what is it a concatenation of? Well, there's an implied concatenation here. And what's this is a star. So what's this? It's a star. And whenever there's a star, you get to choose. What do you get to choose? A value r, right? And then for each r times, you get to choose some string from here, right? And so this is going to be all right. So is this in the an example? What's in the string in the language? Right? It's a bunch of A's followed by a bunch of B's followed by a bunch of A's followed by a bunch of B's. Right? And you just note that this bunch of B's happens to have no B's in it. Right? So tell me another string that's not in here. Can you so what's this? This is all strings of A's and B's, right? Of any length. Yeah?
You said in this example that the last B, there's just no B's, right?
Right.
So if you give me something like this, let's say we're making a machine or something, and I'm trying to write a condition to accept.
Yeah.
Am I expecting to get, what am I expecting it to end in? How would I condition for this?
This, I would call this a block of B's. How many B's are you allowed? You're allowed R B's for any positive integer R. R could be 5, then you have 5 B's. R could be 0, in which case you have 0 B's. Right? So this string is in there. Well, I could also put a few B's here. That would also be in there. I could also have this be 0 A's. Those are all choices that I can make. Right? But can somebody tell me a string, an AB string that's not represented here? No? Nobody can? Yeah? A, B, A, B, A. Exactly. Look at this. This this can come from here, right? And this B can come from here, and this A's can come from there, and these B's can come from there. But where do you get that next A from? Right? This here is specifically a block of A's that could be empty or could have lots of A's in it, but it doesn't have any B's in it. Right? And then we concatenate on a bunch of B's, which could be empty, but, right? So is this accepted? Yeah, because I got some A's and then I got some B's and then the other two are empty, right? But here I got some A's, some B's, some A's, some B's. How do I get some more A's? Right? Everybody buy that? So you guys really got to study some more. All right, so here's a really ugly example, right? In fact, the DFA was ugly. Yeah?
Might put like a bracket around all that and a star. Would that be the same?
Yeah, what does everybody think? Is this the same?
We have to keep the same pattern that we wrote before by adding an A at the end. But then you can repeat that pattern.
Yeah. So is it the same?
Yeah.
Yes. I would say that it accepts the same set of strings, but I would say that the parsing was different, right? Because on top of this, there's this star, which I can do some number of times, right? Here, I would say there's a star, right? And each is a union. I either do an A or I do a B, right? So each of these becomes, right, this one's A, and this one's B, and this one's A. But when I'm doing this parsing, if I have a bunch of A's, a bunch of B's, and then a bunch of A's and a bunch of B's, and then I'm going to break it. And then I'm going to do, again, A, B, break it. So the parsing is going to be slightly different. You can take any string of A's and B's, and what you do is you break it into blocks, where this block is a block of A, a block of B, block of A, blocks of B's, and the same with this one, right? So the syntax, meaning what strings are you allowed in your language, is the same. But I might say the semantics of what does it mean, right, meaning, right, is different. Right? Does that make sense? It tells you how to break it up and think about it. Everybody good with that? So I don't know whether doing this one is, as I say, the DFA that it came from is ugly, and this one's ugly. But what do we have? Well, we have a star which can have as many of these weird things as you want, right? And what is this weird thing? Well, the union is either going to be a single zero by itself, right? Or what it's going to be a kind of a then here we have another star. Oh, I guess we have a 1 in front and a 1 at the end. And over here we go 0, bunch of 1, 0. And then again you go 0, a bunch of 1, 0. And then you go 0, a bunch of 1, 0. Right? And then you end with a 1. Right? So that's kind of the thing that then gets repeated a bunch of times. All right? People sort of follow that? Right? The parsing is, right? This is, what's this? This is a 0, 1, 0. This is a 0, bunch of 1, 0. This is a 0, bunch of 1, 0. And you can repeat that as many times as you want, and then you can end with a 1. right? What is there anything? I would have to think for a while to find a string, a 0-1 string that wasn't in there, right? I mean, you can say here, this gives me an even number of zeros, so it makes me think I got an even number of zeros. But over here, I can stick in as many zeros by themselves as I want, right? So that's false. Right here, I just don't know what's not there, right? So it's ugly. Do people understand these various examples? I would say that this is a good thing for you to study, right? In your life as a computer scientist, regular expressions will come up. In fact, I would be amazed if they haven't come up in your life already, right? And it's good to know what set of strings they represent, and it's good to think about it in terms of, well, how do I parse it and how do I get meaning from that? So could everybody do that? Any questions about this, or should I cover another topic that I think would be good to cover? Everybody good with this? All right, so this proof here is, if I guess the various things that we've done that people find a little hard, this might be something worth reviewing. And one of the things I did over the week is I changed the proof slightly, and I made another one. So we can, another example of the same proof. So we could go over those. So we might as well start by, I kind of hurt my toe on the way here too. All right, so we can start by doing this. So here we have a machine, right? So this is an NFA. It's a non-deterministic finite automata. Why? Well, to be a DFA, what do you need? You need that for every state, there's exactly one option for every character, right? Every state, for every character, there's one option. Meaning if I'm in this state and I get this character, then there's one, not zero, not two things to do, right? And this guy has the problem that out of state 2, if you get a 0, there's nothing to do, right? So if we wanted to fix that, if we wanted to make it a DFA, then what could you do? If you're in state 2, what would happen if you got a 0, really? Well, I heard stop, but I'm going to go no one stop because the DFA is always going to keep reading the string to the end no matter what, right? And somebody else said go back, and I'm like, no, go back where? No. You could go back because at the back there you had various choices and you could make a different choice. So back in that direction. But in terms of this path that you're following, if you're following that path and you get to state 2 and you get a 0, then that path dies. Right? Everybody get that? And what can a DFA do to die? A path. Well, no, because the machine is going to keep reading the rest of the characters and move to different states.
Wait, so your question is like, we're going into 2 with a 1 instead of a 0? Like it's expecting 0 and we're going in with a 1 or something like that?
You're in 2 and you get a 0.
Okay. Oh, so for us to move on, we need a 1.
Yeah. Yeah, but if you're in 2 and you get a 0, then what does the NFA imply? The NFA implies that you go off into outer space and nothing useful is happening, right? But if we want to make that into a DFA, what do? Oh, you guys, we really got to study some more. Exactly. Here I'm in 2, and I get a 0, right? So let's go down to a dead state. And what does the dead state do? It just reads the rest of the string, but doesn't accept. Right? Does that make sense? So for a bunch of those, we could go into the same dead state. Right? What's the other thing about this machine that makes it an NFA and not a DFA? What? Exactly. So the first state, if you get a 0, you have a choice. And that mistake we can't fix easily. Right? You're really going to need a very different machine because that's the point where I say, oh, what you need there is a fairy godmother to say, I'm reading, and what does she do? She tells you to move forward just when the 0101 comes, right? And you can't look ahead, so you can't see that yourself. Right? Does that make sense? All right, so anyway, that's the difference between an NFA and a DFA, which you should know and understand. All right? And so one of the things that hopefully we'll cover at some point, but we are falling further and further to behind, is how to mechanically take a DFA, an NFA, right, and mechanically compile it into a DFA. All right? But that won't be on the test. I've made up the test. I know it won't be on the test. But what might be on the test is I give you an NFA, and I ask you what language does it compute. And then I could say, don't do the mechanical converting, right? But give me a DFA for this machine, right? So you're doing it kind of yourself. You definitely are going to be, on the test, is going to be, I give you a DFA, what is the language? I give you an NFA, what is the language? Can you prove that's the language? Right? Or I give you a language, can you give me a machine? Can you give me a DFA? Can you give me an NFA? Right? Can you, or I give you any of these things, and can you express it as a regular expression? Right? Or I give you a regular expression, can you build a DFA or an NFA? Right? So we very may well skip the proofs of formally converting one to the other. But, you should be able to do it just kind of on your own. Other things that we're going to cover on Wednesday, whatever our days are. What are our days? Whenever we have Tuesdays and Thursdays, we're going to cover some more things which will be on the test, and we'll talk about that when it happens. Yeah? Uh-huh. If you're supposed to build an NFA, then you draw a picture like that. If you're supposed to draw a DFA, then it's kind of like that, but every edge, every node has a, right? Exactly. And you know how I really insist on you doing it is thinking about meaningful names for every state, right? So here we're going to go through this proof, and we're going to think about what are meaningful names for states and what they represent the set of strings that will reach them. All right, so anyway, any questions, or we're going to go through this quickly here, this other proof. All right, so here let's make sure we know what everything is. M is this machine, right? This L is the language of 0, 1 strings that contain 0, 1, 0, 1, right? That's what L is. L of M is what is the language that this machine accepts, i.e., what is the set of strings? A string is in this set if there exists a path to the accept string, right? And accept straight. So what we're trying to do, what are we trying to prove here? We're trying to prove that for every string, in fact, I think, right? For every string, we want to prove that if there's a path in the machine to an accept state, that's true if and only if the string is in this language, because hence it contains a 0, 1, 0, 1, right? Over here, we're talking about machines and paths, and here we're talking about strings that have this property, right? And we want to prove they're the same, right? So holler if I say something you don't get. So what's the first proof? It's going to be loop invariance, likely on the exam, that describes the set of strings. So, right, we want to get the set of give names to the states, right? And the names are going to describe the set of strings that have passed to that state, right? And it's kind of what the DFA knows when it's in the state, right? If I'm in some state, what do I know? I know I got there, right? So I know that it's one of the strings that has a path to the state, right? That's all I know. Does that make sense? I don't know. I don't remember anything about the past. All I know is I'm in the state. All that tells me is that the substring we've read so far has a path to this state. And we're going to do it by induction on the length, right? We're going to focus on each state and each time step. All right? So here I added this slide to clarify what we're talking about, right? We're talking on one side of the divide, we're going to talk about machines and their paths and what strings label those paths, right? And so for each state, we're going to define, before I used, if you definitely, whenever, periodically re-download anything that I have, because you know I change them all the time, right? So in the old version, I used L for this, and I used L prime for the next thing. And I decided that it's better to use M here because we're focusing on the machine, right? So here, what's M of a state? It's the set of strings that have paths to that state, right? So we're talking about the machine. Right? And what is it? It's a definition. If we take we build a new machine. What's our new machine? Is you take this machine and you make its only accept state be QI, then that's the language the machine would accept. Right? Does that make sense? Everybody following? If you're not following, holler, because we have a test coming up and I want you to all pass. All right, so here we're talking about paths, right? Everybody, it's all about what there's paths to, right? And so here is an example. We just proved that 0, 0, 1, 0 has a path to state 4, right? Everybody buy that? I mean, why? Because look at, let's hear. We start there, we read a 0, we read a 0, we read a 0, we read a 1, we read a 0, we're in state 4. Right? Everybody get that example? All right, so here on the other side, we're talking about languages and properties of strings, right? So for each I, we're going to talk about the L of I. But you remember before it was L prime, but now it's L. The L of I is some set of strings with a bunch of properties, right? And so again, and our goal, what is our goal? Is to prove that these sets are the same, right, for each state. And when you're trying to come up with this property, one thing, maybe you know the language and you're trying to build a machine, or maybe you know the machine and you're trying to build the language. Either way, I think the best way to do your task is to imagine some substring, right? Try to think which substrings are interesting, right? Just try to think of interesting substrings. Here is a substring. I can think, if I've read that, what does the DFA supposed to remember, right? Because it can never go back and look at it again, right? So what does it need to remember about it? And then we have a state for every different possible thing that you might be remembering, right? Does that make sense? For this state, the L of this state is, I'm remembering that the sky is blue, right? Now in this state, I'm remembering that the sky is gray, right? So what do you want to remember about the substring? What does Pooh Bear write on his blackboard, right? Here, what do we want to write on the blackboard? We want to remember that it ends in 0, 1, 0. Right? Why do we want to remember that? Because it's useful in the future. Now it's not useful, right? But in the future, if we get another 0, another 1, then that's useful. Right? Does that make sense? So here, we got written on the Pooh's blackboard that it ends in 0, 1, 0. Right? And what's common about all the strings that arrive in that state? Right? All the strings that arrive in state 4 will have this property that they end in 0, 1, 0. Right? Does that make sense? And you can see if I gave you the machine and you needed to figure out what it means, this is a useful thing to do. And if I gave you the language and you needed to build a machine, then this is a useful thing to do. Right? Everybody good? Right? So we can give names to these states. Right? And so this is just what we did before. Right? We give name to each of these states. This could be... Now, here's another thing that you should remember. Right? If you're making really notes here of things to remember, when you're doing this for a DFA, do these sets need to be disjoint? Yes, right? Because each string can't be in the set for more than one state, because each string arrives to only one state. Right? For each string, which set is it in? It's in the set associated with the state at which it arrives. And so those are disjoint. Right? And in that case, you want to be able to say, well, it ends in 0, but it doesn't end in 0, 1, 0. Right? You put those doesn't so that you make them disjoint. Does that make sense? But if it's an DFA, then a single string can arrive at more than one state. And so the sets don't have to be disjoint. Right? So we can have a state, the first state, any string can arrive in the first state. Right? In the second state, well, it's got to end in a 0. Right? Because if your last character was a 1, well, you didn't arrive there. Right? And then the next one, it ends in a 0 and a 1. Right? Everybody following that? So, right, so this is just what we said before. And now, how are we going to prove what do we want to prove? We want to prove that for each state, for each string alpha, if the alpha is has a path to that state, then it has the property for that state. right? And here we're going to break it up into, I call it loop invariant sub T because I love loop invariance, but it really is induction, right? This could be our induction hypothesis for T. Our induction hypothesis is that we have the right answer for all strings of length P, right? So given T, we want to say for every state, it doesn't matter which state you're talking about, for any string alpha that has length T, because we're only considering alphas of length T, then that string alpha has a path, is in MQI, has a path to that state, if and only if it has the property for that state. Right? Everybody get what we're trying to prove? And the proof I have here is going to be short, which is suitable for, I think, for a test. When we do it next time, in 5 minutes from now, it'll be a little longer. I'll give you more details. And I was thinking about coming back and changing it here, but it doesn't really fit on the screen. And somewhat the other difference is we have little effects at the top, so you can see them. All right? So here, we want to start with the base case, right? Here, this is just saying, you got to prove it for the base case, and then you got to prove that if it's true for T, it's true for T plus 1, right? And how do you do the base? How do you do the base case? You just have to say all strings of length 0. Well, how many strings are there of length 0? Only epsilon, right? So which states have paths of epsilon to them? Well, in this case, it's only the first state, right? Only the first state and not the other states. And which of those strings, which of those languages there contain an epsilon? Well, the any string does, and all the others don't. Right? Does that make sense? So that's how we do it for the 0 case. Right? People buy that?
So for the epsilon, it can be contained in any state.
Well, one of the things that we haven't covered yet, and we can cover it right this very minute, if this is the start state, there's these things called epsilon transitions, which means that you can follow them without reading anything. And in that case, the empty string has a path to here, and it has a path to each of these guys. Right? But in this guy here, we don't have any epsilon transitions. So if you have the empty string, the only state that has a path to empty string is the start state. Right? And given we haven't, we're going to cover, this week we're going to cover these transitions. All right? Everybody get this? So now what are we trying to prove? We're trying to prove, suppose the loop invariant is true, the induction hypothesis is true for T, and we want to prove it's true for T plus 1. Right? And so how do we prove it for T plus 1? Right? This is just saying, what do we know? We know that for every path of length T, we have this property. Now we want to prove this. And so if we want to prove this, we're trying to prove this statement right here for T plus 1. And since we all know about first order proofs, the proof is going to say, let I be an arbitrary state. Let alpha be an arbitrary path, arbitrary string of length T plus 1. And then we're going to assume this and prove that, or assume that and prove this. Right? Both directions. Everybody got that? How you do these proofs? Right? Not that you learned this in 1090, but you should have. Right? And I'm going to do it differently next term. All right, so here we go. How do we prove this? Well, now what we should be doing is we should be saying, let I be an arbitrary state, right? But instead, I'm going to do one example, right? We're going to do each of them separately. So let's just consider state 5. And then now we want to get an arbitrary string of length t plus 1. And what I'm calling it is alpha c. Why? Because alpha will be of length t, and c will be of length 1, right? So alpha c is of length t plus 1, right? You didn't catch that before? Anyway, that's right. Everybody get why we're doing alpha c? Right? So this is an arbitrary string of length t plus 1, right? And what do we must prove? Well, we must prove that if there's a path to it, to length, to state 5, then it has to have the property for 5, right? If and only if. Right? And so if it has a path, right, there's a path, then it has to have the property. Right? Everybody following this? So there's our property. We wiggled it. So now we're going to just crank out a proof. Now, let me tell you, in a general rule, when you're trying to prove if and only ifs, there's 2 ways of doing it. The one is you assume the first thing, and you say hence and hence and hence and hence, and you get the second thing. And then you have a second proof, which assumes the second thing, and go hence and hence and gets the first thing. And sometimes I find that it's best to do them separately because the proofs take slightly different forms, right? And sometimes they take the same form, in which case you can do the first thing if and only if the second thing, if and only if the third thing, right? So what I do in practice, especially in a test where I don't have enough time, I start by thinking about one of them. I'll say this implies this, implies this, implies this. And then as I look at each imply, I'll think, does this actually go in both directions? And if it goes in both directions, you change it to an if and only if, and maybe you get both proofs for free. Right? Does that make sense? So here, well, if it's in that set M, then it has a path of length t plus 1 to Q5, right? And is that an if and only if? Yeah, it is. It's the definition of M, right? That's just a definition. Everybody good with that? Right? And then we want to say, well, what does that give us? Right? Let's look at the machine, and we say, well, what are the edges coming into 5? And there's 2 edges. There's the edge coming from 4 and the edge that's staying at 5. Right? Does that make sense? And so we can say, well, if AC has a path of length t plus 1 to here, then what do we know about alpha? Alpha has a path of length t to the previous node, right? And so it either has a path to Q4, and C better be 1, right? I missed that in the slides before, right? If alpha comes to 4, then to get to 5, you need C to be 1, right? Or alpha goes to C5, but we don't care what C is, right? Everybody buy that? And is that an if and only if? Yeah, you check, if and only if, right? If this is true, if alpha has that property, then alpha C has a path to 5. And alpha C has a path to 5, then it gives us that alpha has this property, right? So everybody see that that's an if and only if, right? Right? And then that's just here we're sticking it in the picture. I remember I told you we throw in some pictures to help us along. All right? So now we can then say, what do we know about this is where we're skipping some things in the proof, right? Well, the loop invariant then tells us, right, well, if alpha has a path of length 5, then alpha is at MQ4, right? Or is it in Q5? And our loop invariant then connects it to the L's, right? So anyway, what we're saying here, by the loop invariant, here, I think I will change the slides to have more steps in here, right? The more steps would be, hence, alpha is in MQ4, right? And if alpha is in MQ4, then by the loop invariant, alpha is in LQ4. And if alpha is in LQ4, then alpha ends with a 0, 1, 0. Right? Does that make sense? Right? Similarly, if alpha has a path to Q5, then alpha is in MQ5, and hence by the loop invariant, alpha is in, because it's only of length p, it's in LQ5, and hence it contains 0, 1, 0, 1. Right? Does that make sense? And in this case, C is a 1, and in this case, C could be anything. Right? So now we can go back to talking about alpha C, right? So now what we can say, well, that alpha C, well, if alpha ends in 0, 1, 0, and then C is a 1, then alpha C ends in 0, 1, 0, 1. Right? And if alpha contains a 0, 1, 0, 1, and I put another character on the end, it still contains 0, 1, 0, 1. Right? Does that make sense? And so that's an if and only if alpha C is in the language of, say, 5. Right? Is that making sense? Can everybody do that on a test? Yeah? DFA proof too.
But then there would be two options that C equals to 0 and C equals to 1. Because each state has its own way.
I'm going to go with no. So I'm going to say that so what changes if this happens to be a DFA? All right? The only thing that changes is that those L sets have to be disjoint. All right? Everything else in the proof is going to be different. Now, you might be saying, well, given a state, it has 1 leaving 0 and 1 leaving 0 and 1, right? But that's kind of not what we're doing here, right? This part of the proof says what's coming in, right? And there could be a number that are coming in from 1 and a number that are coming in from 0, right? So what I have to say is I say if alpha C has a path to here, then alpha has a path to here and C is 1, or 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 to here and C is 0, or here and C is 0. Right? So that can be true for a DFA just the same. Right? Does that make sense? All right, so when we're going on here, what we're doing is we're trying to make it a more general proof. Right? Here's a more general technique of the relationships between the L's. Right? And if you have this relationship, then we can do this proof for an arbitrary state. Right? So you can play with that. All right, here's a question now. I can do another example of this, or I could leave the other example to class, or we could do another example right now. something that you came up with.
What exactly is, like, what are the differences between DFA and NFA? Because they look exactly the same.
They certainly look similar. Anybody want to answer the difference? So, in fact, let's get you to answer the difference. I will put various things on the board, and you tell me whether they're a DFA or an NFA. So, if I have a state here, does this look like a DFA or an NFA? No. No. It's non-deterministic because if I'm in this state and I get a 1, what? It doesn't matter. This could be any state. Any state. If there are two edges leaving 0, saying 1, then it's not deterministic. So in this case here, there's one edge leaving 1, labeled 1. So if I'm in the state and I get a 0, it's deterministic which state I go to. And here, it's non-deterministic which state I go to. Right? And so this is the big issue. All right? Here, you kind of need, I like to have a fairy godmother tell me which way to go. Right? Now, there are other differences. This state could have no edge leaving 1s. So if you get a 1, then you kind of die. Right? So that's a difference, but it's not a difference that matters so much because I can always fix it by going to a dead state. All right? So that's a small order difference. This is a big order difference. Another difference is that in NFA you can have these epsilon transitions, and that's non-deterministic because if I'm here and I get a 1, I have a choice. I either can go this way and follow and read my 1, or I can go this way and not read my 1 and read my 1 later. Right?
So that state, is it only for NFA?
Which? This? This you can have a dead state. Any machine can have a dead state. NFAs tend to not have dead states. They tend to just drop you in the garbage when they want you to be dead. Right? Well, a DFA has to be polite. It has to move you to a dead state and take care of you until the end. Does that make sense? What do people want to do now? Parsing string? Well, we kind of did that here. Do you want to do some more of that, or more examples? More examples of parsing strings. All right. Can anybody think of a language? How about everybody? The number of 1s is odd. All right, so everybody right now, write down a regular expression where the number of 1s is odd. All right, has everybody done these? Number ones is odd. How are you going to do that?
I'll have like a 1, and then I'll have whatever kind of string I want, and then I'll also add 2 ones that have to be repeated. Or yeah, have that. Yeah.
Is that what you're doing?
This is not correct.
Well, some kind of string, what I mean by some kind of string is like a string that's not 1 in the middle.
Oh, this one here?
Yeah.
All right, so so right here, right, we could have any number of ones. So that messes up our life.
So what I meant was in that string you just only make it zeros, so you can only have whatever number of zeros you want. Yeah, something like that. So that would be
All right. So a good game is if you have two sets and you want to see if they're equal, you say, can I find something in this set that's not in this set? Can I find something in this set and not in this set? All right? So here, I can say, can I find me a string that has an odd number of ones that's not represented? Right? Or you could say, is there something represented that doesn't have an odd number of ones? Anybody give me an example of a string in either direction? Yeah? 1, 0, 1, 0, 1. Right. Exactly. Because here, this says all the zeros have to be together. Right? Once I get a 1, I can never have zeros again. Right? So, right here, I get this 1. I get a bunch of zeros. But
okay. That's easy to fix. Just put a 0 in the middle of the 2 ones and have as many zeros as you want, and then
where?
in the 0 in the middle.
Here?
Yeah.
Okay, well, but you know your job is to give me regular expressions. So tell me the actual regular expression that we're doing. Well, you can't use English words. You can say zeros and you can do stars and you can do concatenations.
Okay, so 1 and then 0 star.
Yeah.
1 and then bracket star. 0 and then star. At the beginning I'll add a 0 star as well.
Excellent. Excellent. Right? When you didn't have here, what was the problem? Had to start with a 1, and that's no good. Right? So this is really quite good. What is a string? Well, it can have any many zeros as you want. And then there's a 1 followed by any number of zeros, followed by a 1, followed in by many zeros and a 1. And it comes back, this 1. Oh, I still see a bug.
I guess so. Remove the stars for the first 2. No.
Where's our bug?
Just repeat like the first 3.
Let's make sure everybody gets the bug here. Is that here, right, I'm doing this star thing, and down in this one, I got a 1, 0 star, 1, right? And then the next one, I get a 1, 0 star, 1. And what is it requiring that these two ones have to be together?
Yeah.
What we got to put zeros here.
Yeah. Okay.
Yeah. We put a 0 star here.
Okay.
Then that gives us, right? It's saying it begins with 0 star 1. Right? Here's our 0 star 1.
Is that a problem?
Oh, and 0 star. Right? What?
Is the problem right there? Is that a problem? The 1 in the beginning
No? Why is it there?
I put it there just to make sure
It's
odd.
It's odd, exactly.
Yeah. But like, would that break what you're trying to prove? Because like, I can't have as many ones. I guess you don't have to have the zeros, and then it'll be easier.
Yeah. Yeah. So I claim this is good, right? and why is it good? I'm going to say, take any string of zeros and ones that has, right, that have an odd number of zeros, an odd number of ones, and you kind of break it, right? Here we've got a bunch of zeros and a 1, and a bunch of zeros and a 1, and a 0 and a 1, right? We break it in front of the even 0, in front of this one, and then we break it in front of this one. So this is the first one is going to be this one here, right? So let's label the ones number 1 and number 2 and number 3 and number 4, right? And so let's break it in front of the ones that have an even index, right? And then what is our block in between this break and this break, right? Well, it's going to begin with a 1 because that's where I put the break. And then it's going to have 0 or more zeros, followed by a 1, 0 or more zeros, followed by a 1. Oh, no, I break it before that. Right? Does that make sense? And so this is exactly what this block is doing. Right? Does that make everybody buying this? And then what do I have at the beginning? Well, I have to make it even. Odd. Right? This is going to be an even number of ones. We have to make it an odd number of ones. So there's our odd. Well, before we don't want it to begin with a 1 necessarily, so we can put any number of zeros before it, and we can put any number of zeros in between, and we don't want to have it to, here, this guy here, do we need that now? No. We don't need that. I mean, it doesn't do us any harm, but we don't need it because we can get the zeros from our last guy. Right? Does that make sense? Everybody buy that one? All right. Oh, this one contains 0, 1, 0, 1. Somebody else want to give me a regular expression for that? Right? Everybody buy that? How about it ends in a zero block of a non-zero block of zeros. And that non-zero block of zeros has even length.
Wait, what does that even mean, non-block of zeros?
So we often break strings into blocks. And so one block would be break it into, if I have a string, the one way to break it is into blocks of zeros and blocks of ones, right? And so if I'm talking about blocks of zeros, then why did I say non-empty? Right? Because we want to distinguish between empty blocks and blocks that actually have letters in them, right? So we want a non-empty block of zeros. So here, this doesn't end in a non-empty block, right? And that does, right?
Is 1 0 considered a block?
1 0?
Like if that 2 zeros was just 1 0.
Yeah, 1 0. That's a block of. I consider this a block of zeros, right? It's a block of zeros of length 0, right? But most of the world might not. So just to clarify, If I want to clarify that I want my block to be non-empty, right? I'll say it's not. And non-zero is confusing because there's a zero twice. Yeah, so non-empty is much better. Yeah, for sure. All right, so now how are we gonna get a regular expression for this? Well, anything that ends in a zero. There. That's anything that ends in a zero. Yeah, one, it doesn't have length even, and two, you're not including this guy of length 4.
Wait, 1 second. How am I not including that? Because so everything is covered. Everything is covered with a 0, 1, right? Repeating over and over again.
Oh yeah, right. This includes all of that.
Yeah, and then I just add a 0 at the end to make sure that the last thing is 0. The last block is going to be 0. So if there's already 20
But
there,
it covers things it shouldn't cover. It covers this.
yeah, which is a block of 0. Ends at a block.
Not of even length.
Oh, okay.
Sorry, yeah, you're missing this part of even length.
Okay, so we can just do 2 zeros then.
Okay, what about this? What does that include? That includes this.
So we'll call just having a 0, 1 just in the block. I mean in the bracket, just 0, 1.
What, this?
No, in the bracket, just 0, 1. Just no dots, just 0, 1. So
That's what I have here.
just no dot, just 0, 1.
He says no zeros at the end. No star.
No, in the bracket, just 0, 1.
This here?
No dots.
That's a comma, but okay.
So you would manage all the strings.
So that's going to hurt us more. If we want to get length, they're going to be alternating like this.
So that's given.
We can't get a bunch of ones in a row.
Bracket 0, then y star 0, bracket star, then 0, 0.
Sorry, what are you doing?
Bracket 0, y star. No. 1 star. Y star.
So 0 star.
0, y star, then 0, then bracket, then star.
I have to open and close my brackets.
Opening and
Put the bracket at the beginning,
yeah, the beginning.
and then close it there, and then
Bracket,
start.
then star. Then enter 2 0.
Um,
But then you can't have any more zeros in the middle.
that certainly has an even number of zeros.
Not necessarily even.
But actually it's kind of funny, it ends with, here it concludes 0, 1, 0, 0, 0, for example, and that has an odd number. Right here we get that, and
Put another 0 in the bracket.
Put another y star before the first
Get rid of
zero.
one of the zeros.
One second. I have a question. So when you say even, do you want the whole thing to be even?
no, the block it ends in a zero, non-empty block of the zero. The block of 0 has even length.
Okay. So, why don't we make sure that we
Let-
have 2 zeros and then a star 1 for them?
So what are we doing?
The same thing you have at the top.
Just
to make sure there's a star 1. So yeah.
Here, where are you putting star 1?
So after that bracket,
After this.
yeah, have a star 1, and then just 2 zeros.
Well, that's first off, this. All right. So what does this include and not include? I,
It includes
it,
any string.
can it include this?
Yes.
Yeah. At the beginning.
No, it's saying that.
Can it include this?
Yeah.
Yeah, at the beginning.
No, but I mean, this could be the whole thing,
It's gonna be. Oh, we're gonna include this. Oh.
right?
No, it
I
can't.
just make this 0 empty,
Yes, it can. Yeah.
and I get a 0 from here.
Yeah.
But that's odd length.
Take out the star and yeah, I guess take out the star and the zeros should be in brackets and then star.
So what do you want? You want this?
Oh, so he wants to remove the star.
So, why not? Yeah,
Take out the star.
this star.
Yeah, and then have 0, 0, and then next to it have bracket 0, 0, bracket.
And next to it we put.
Brackets. Yeah. I guess there's so many ways to use it.
How do people like that?
There's no need for the 2 zeros in the middle. Except 0 is
There
0
is
is
this
even.
non-empty
Yeah.
block at the end. So if you don't have the 2 zeros, then that might be empty at
No,
the
but
end.
that's okay because they're come in sets of 2, so it's always gonna stay even.
Now, so the 1 here I like because it says this here will definitely be a block of zeros, right? That is our last block of zeros. And anything that comes before that 1, I don't care about, right? But what do we got here? Well, how many zeros are here? Well, it's even, and it's not empty, right? If you didn't have this, then you could get non-empty, right? Everybody like that? Now, here's a question. Does this include, I'm happy that this includes everything we need. Does it include everything we want? No, does it miss things? Yeah, it does include everything we want. Everything in there ends in an even block of zeros. But where does it missing? Yeah. Yeah, if it's just this, this doesn't include that. Right? So how are we going to fix this? No, because then you could get 0 of them, and we go back to our previous problems.
Before 1, 0 star.
Before here? Well, if that 1 is there, you're going to still force there to be a 1. Yeah?
Can you have a bracket for the another bracket in the beginning and after 1? Yeah, you put a star. Oh, sorry, a star after the closing bracket.
Ah, here. Yeah, actually that works. That works. I was going to just speak, right, because then you can remove this if you want. Or you can do it many times if you want. I was going to do something else. I would do the empty string union with this, right?
So is it with every, like with the 1, like empty string or 1?
Yeah, this here is, you have to know how to parse it. This is empty string or this stuff, right? So here, I mean, the implied brackets are here, right? So at the beginning, we can have anything followed by 1, or you could start with nothing, right? So what's this? This is anything that ends in a 1. This is nothing. This is, you could choose between those. And what do we have here? We have a non-zero block of an even number of, non-empty block of an even number of zeros. Right? Everybody buy this? So, the next one we were doing, yeah?
Just the 4 zeros, it won't work. Yeah. If you just have 4 zeros.
Because it doesn't include 6 zeros. Right? This includes 2 zeros, or 4, or 6, or 8, or 10.
The number of 0 at the end is even here.
Yes. Yeah. Oh, did I say odd? Oh, no, it's even. This one? Oh, no, we haven't started this one yet. Now, what did I change? I changed the last block, the last non-empty block of zeros has to have odd length. All right, so what are we changing? That means it's ends in that. But what else, what other string should we now include? What about this? Does that get included? What's the last, right? Here it's saying that the last block is of zeros, right? Here it's talking about the last block of zeros. See the difference? I mean, it's a subtle English shift. Well, let's first make sure people understand this. Everybody understands how this is the last block of zeros. Right? And it has to have odd length. So we have to be able to include this. Somebody said something and I didn't listen.
Yeah, I said we add 1 star at the end.
Yeah, exactly. Exactly. Right? Exactly.
But then, doesn't that break the whole point of this whole thing? Because we want to end with an even block of zeros?
No, we don't though. Now here we wanted to end with a 0 block. Here, the last block of zeros. Right? It's different. What's our last block of zeros is this. This is the last block. Right? Yeah, and it's of ones. So the last block has ones in it. So this says it wasn't good. Right? But the last block, this is the last block of zeros. Right? Are people whose English isn't your first language getting the difference here? This is the last block, and it's of ones. Right? This is the last block of zeros. Right? Everybody getting that? All right. How are people doing? Yeah? Oh, you're doing this one here? All right. What's your answer?
Open bracket, 0, 1, close bracket, star, 0, open bracket, 2 zeros, close bracket, star, and open bracket, 1, close bracket, star.
All right. You have the problems here that you're not telling me I have to have a 1 here, right? So I could have 1 0 from here, and then zeros from here to get. I can get 4 0. I'm going to get a 0 and a 0 here, and then a 1. Now I have an even number of zeros, right? So this is the answer that I was thinking. Here we got it right at the beginning, right? This guy ends in a 1 or nothing, and then we have an odd number of zeros, and what we add in the end, thanks to the guy over there, is that you can have another block of zeros if you want. You don't need it, but you can have it if you want.
So if you remove that last one, isn't this the
If this here, if you remove this, then the last block has to be a block of zeros of odd length. So you get the difference between the last block happens to be of zeros versus the last block of zeros. No, yeah, I had this fear that it was a subtle English difference. You know, I have to tell you, I have so much sympathy for people whose first language is in English and they're coming in here, and you got to listen to me talk so fast. I mean, it's just how you got to. Here? Yeah. All right, so I'm not a good English major. I'm not good at poetry. So often I'm struggle between the differences, between subtle differences between two sentences, right? I've definitely had that problem. But this one, you have to say is there a verb to this sentence, right? Here we're talking about the last block, right? And let's do an example. Right, so here, what's our last block? This is our last block, right? It's talking about the last block. What's true about the last block? Verb. The last block is what? It is of zeros, which is not true here. Right? Does that make sense? All right, here. Right, what are blocks? They're all the same letters. Right? Which is the last one? This is the last one. Right? So we're talking, our subject is this. Are we running out of time? Okay, I got to go to class. Okay. Let's finish this. You can anybody leave if you get the English, but if you're not getting the English, you should stay for another minute. Right? This is the last block, right? And here we're using a verb is to say the last block is of zeros.
So that means that it ends with zero.
Yeah, it ends with zeros, right? This one says the last block of zeros, right? We don't have a verb here. Right? We're just saying the last block. This is the last block of zeros. Right? Does that make sense? I know it's very subtle. So I apologize for that.
Quick question. For the first example, you said the number of ones is odd, right? And so you gave this as the answer?
Yes.
I wrote this. I just want to know if that's right too. So you put 0, 1 and then an asterisk and then you put a 1.
The stars? Well, this could have an even or an odd number of ones in it. So we can't assure that the number of ones is odd.
Here, this one here is an odd one, right?
Yeah, but that could
That's
give
like
me,
defined.
this could give me 1, and then that will make it even. Right? Here, let me.
Just a quick
Okay, no, let me turn this off because